Tēnā koutou katoa. Welcome to the Seismic Design for Building Services training session. Before we begin, I would like to take a moment to recognize the traditional owners of the different lands, countries, and places that all of us are engaging from today. I know that most of our attendees are from New Zealand, but we also have some Australian colleagues joining in. Welcome, welcome. On this slide, we are showcasing Ngātarangi Mine Bay Maori rock carving on Lake Taupo, which is one of the most extraordinary Maori artwork created to remind us of a connection between our families and the land we come from. There are a couple of announcements about the upcoming CIBSE events to make. One of the most anticipated events will be this seminar series that will kick off on the 22nd of August. What I like about this series is that they run online. They include over 20 industry leading speakers and panelists. Each session is only 2 hours, which is easy to fit in your schedule. And on top of this, everything is recorded. So if you miss any session, it's very easy to replay it. I highly recommend attending this event. And the next event to mention is organized by Young Engineers Networking Group. If you're in Auckland, please join us for some social pin bowling next Wednesday. CIBSE would like to thank Connexus Recruitment for supporting CIBSE NZ annual program technical seminars and Young Engineers Networking events. Connexus is a boutique recruitment consultancy specializing in building services design and sustainability. We have a strong presence in Australia and New Zealand design and construction sector. We connect top design consultancies, contractors, and clients with global talents. And now we have arrived to the main presentation by Chris Somerville, who is a New Zealand structures team lead at Jacobs. Chris has an extensive knowledge in seismic design and structural engineering. He's one of the most passionate and talented engineers I've ever met, and I cannot wait to hear his presentation today. And so without further ado, please welcome Chris.
Thank you, Anna. That's a great introduction. And yeah, thanks for the compliment. You're making me blush already. So, all right, I'll just jump on and share my screen now. Hopefully you can all hear me well. So,
yep.
So yeah, so sort of as Anna touched on, I lead the structural team at Jacobs. I've got about 17 years experience, just over that. I've worked in the UK, if you can't tell by my accent, for a good portion of that, and then I've worked in the Middle East, and for the past 7 years I've been in New Zealand and worked on projects across New Zealand. I've been involved in seismic restraint design for residential and commercial projects, as well as some large infrastructure projects such as City Rail Link. So I was on that project for about 2.5 years, going through each station. But more recently, since joining Jacobs, I'm looking at data centers, sort of heavily serviced buildings and stuff in the power industry. So yeah, it's a slightly different scale on some of the stuff. So right, next slide. Oh, there we go. So sort of done the introduction. So today's talk, I'm going to sort of split it into 2 parts. The first part will just be giving a general overview of seismic restraints and what the aim of this presentation is. So we'll touch on what needs restraining, how we do it, and what doesn't need restraining. Surprise, surprise, some things don't, although it doesn't look like that sometimes. And the second part will actually be looking into sort of the seismic restraint strategy. And I've sort of tailored this towards the building services side and what we can do there to try and improve the outcomes of projects. So, and we'll sort of touch on each of those areas in a bit more detail later on. So a bit of an overview of seismic restraints. So it is a requirement in the building code that non-structural elements are seismic restrained, but this has been poorly done and executed and understood over time. It is getting better, but a lot of the reasons around why that's not been done or understood is a key one is there's a lack of planning around it. It's usually an afterthought. It comes in at and it comes in the sort of the contractor stage as well. So it used to be a time where it was always pushed to the contractor. Even like from a structural engineers, we would always go, we'd tag out of it in our proposals, specifically saying we wouldn't be doing it. But that generally leads to issues later on, because as we're getting more intense services and tighter space, seismic restraints really does play a key role in especially space planning of those congested areas. So, and there's always a view that it was someone else's problem as well. So the aim of this presentation, I suppose, is I want to sort of foster a greater understanding between service engineers, structural engineers, architects, because it involves all disciplines and we all sort of have to go along that journey together. So why do we need seismic restraints? Well, the obvious one is safety. We don't want to injure people or cause a loss of life. But we also don't want people to be able to escape buildings. So we don't want the ceilings falling down or the walls falling down in means of egress, or equipment falling through the ceiling. So we've got to maintain that sort of clear escape routes. We want to reduce the damage, so we want to limit the repair costs. We'll come on to it in a sec, but a big bulk of a building's cost is generally in the fit out. The structure, the shell, essentially, shell and core is a small portion of that cost. And there are also social and cultural implications, like seeing some historic buildings collapse and some listed elements of buildings, and that not all play a part in sort of trying to reduce the damage. There's the operational continuity element. So there's two parts. This is commercial elements. They want to limit their downtime, which will then limit their loss of revenue. But there's also in the essential services spaces like hospitals and key infrastructure projects, we want to maintain operational continuity because they're generally the services rely on in an emergency. So, and the other one is better design. What this does, it creates a better outcome for the project. So it allows us to manage change by addressing these issues early. It creates a better collaborative environment. If you can get, because we're all going to have to be in at the start, and it does simplify construction because these things have been thought through from the start. So what can happen? I suppose you've probably seen these over the years, but these are some of the images from Christchurch earthquakes. There was a lot. I think there was 1,048 injuries, and 861 of those were from the Christchurch earthquakes. So that there was a number of things that happened in this earthquake, so that didn't comply. So even though the code was around 4219, things like brace fixings were installed with slide holes. Equipment was suspended within the ceiling, did not have flexible connections. Mechanical equipment weighing more than 10 kg was not restrained. And another key one was some of the equipment wasn't restrained properly, was actually swaying into this ceiling. So it looks like on these images, a lot of the ceilings fell, but some of that is because equipment has hit into the hangers of the ceiling. So, and I like the sprinkler one up here. You can sort of shows the degree of movement the earthquake went through. The cost of seismic restraints. So as I sort of touched on, a bulk of the cost in a building is in the non-structural and the contents. And that sort of, the contents sort of increases the more intense the building is. So like hospitals and data centers, for instance, the contents are quite high. But a small portion is the structural element. So so Opus did a study in 2017, which is quite informative. It sort of goes through, I think there's 6 or 7 different projects that they went through and looked at the actual cost of implementing seismic restraints into the design. And you can sort of see from those values, hopefully you can see clearly, but hospitals, as you expect, would have quite a high cost. But the shocking one, I suppose, is the building refurbishment. Installing these systems after refurbishment, we have it with seismic assessments where we need to upgrade the seismic restraints, is a very costly and timely process. because you know the building was never conceived to have them at the start. So that can be quite a challenge. But the other cost is of people as well. So 61% of the earthquake, this is from 2010 to about 2014, 61% of the injuries sustained were from non-structural. And of those, 16% were from services. So, and you can sort of see the severity of the breakdown as well. So obviously with structural failures, a big portion of those were either fatal or required hospitalization. But the non-structural majority is sort of minor, can be treated on site, and with very few going to hospital. But the cost implications as well sort of have to come into play with it. So how do we do this? So I think the first thing we have to do here is to understand what non-structural means. So these are elements within a building that are not considered to be part of either the primary or secondary structural systems. So the way I always look at this and the way I describe it to people is, if I took out this element, would it cause a collapse that is disproportionate? So a non-structural element, I should be able to take it away and it will only create a very local effect. So it's all sort of written into the building code as well. So we have to comply with B1, which says that non-structural elements should remain stable under imposed loads, such as earthquakes. This requires the design of all parts of the engineering restraint system to have clearly defined load path. This doesn't just relate to seismic, this relates to any kind of actions. So it could be thermal expansion, gravity, any other actions that we see can all play a role. We have to justify that load path down to the ground. So how do we do that? I suppose is the key design codes we look to use. So we've got these are sort of the main loading codes for seismic, 4219, which is mainly for seismic restraints of services. The ceilings ones has its own one now that was upgraded recently, and fire sprinklers as well. That's sort of excluded. The last one there is there's a practice note 19 from Engineering New Zealand that deals with pressure equipment. So if you're dealing in the process environment, that's more for you. I won't be covering that today because it's quite unique, and some of the things in there are quite different to what we have in 1170.5. So, but these are the key ones, but there are a lot more. So all these are support codes that we have to abide by. The last three of those are actually from Australia. So for those from Australia, there are some guidance out there as well. But yeah, I won't go into too much detail on those today. So what needs restraining? I always look at sort of splitting this up into two parts. So you've got the architectural elements, which are your sort of suspended features, I call them. So your big lights, not that we see many chandeliers these days, but artwork and stuff like that. Then you've got your partitions, your FF&E, which is your fixture, furniture and equipment, and ceilings. So they generally fall into I won't be covering those today. I'll be touching on to some of them, particularly partitions and ceilings, but I won't be covering that today. The other part is the services, which is the key part. So, and this covers everything pretty much. So suspended equipment, wall, floor mounted, and then your main linear services, so cable trays, ducting, fire and hydraulics. There's obviously some process pipes and other bits in there as well, but that covers the bulk of it. So when you look into those and you start looking at different elements, there's quite a large list. And the reason for this slide is just to demonstrate that it's quite broad terms, but there is a lot to consider, and most parts of a building will need restraint to a degree, although some things won't. So there are some exceptions. So what I've got here is for a snippet from 4219, and this sort of shows the clearances that are required. So a good one that I always like to look for is cable trays. If I can push cable trays up to within 400 mil of the soffit, I don't need to brace them, which can save me a lot of work and save a lot of money, and everyone's happy. The Pipe as well is a key one. So if you've got pipes that are quite heavy, try to keep them up to the structure, because it will, even if you can't stay within the 150, it'll make the seismic restraint much simpler. So they can be cause quite a lot of challenges down the road. And ducting as well. So ducting within 200 mil doesn't need restraint. There are some weight limits. So the weights I've put in here are from the amended version of the code, the 1170, which is generally considered best to use, although it's not in the building code at the moment. So yeah, there's elements that weigh less than 25 kg and is wall mounted, doesn't need require restraint. Elements that are 50 kg and on the floor don't need restraints, and elements that tethered to the structure to prevent it from becoming a hazard. So as long as the tether is can take twice the gravity load, it doesn't need restraint. The little bit in blue there is actually from the Australian version of 1170.4, no, 8.4, I think. The conditions there are a little bit less onerous than ours in New Zealand for obvious reasons. A key one there for me that stands out is all round air handling ducts less than 700 mil in diameter don't need restraint. So that's quite reasonable. And some of the weights there as well and diameters are quite key. So that sort of gives an overview of what we've got. If there's any questions on that, please fire away. I'll just go chat up as well. So the next part of the talk, I'm going to start going into the seismic restraint strategy. So this is sort of my take on it and how we approach it at Jacobs. Each company will have their own sort of take on it, and some of the terminology might be different. So there's no right or wrong way, but I think it's just understanding what they're after. So there we go. So at the start of a project, I like to develop what I call a project seismic restraint plan. So, and we love abbreviations over here. So the idea of this plan is to basically establish the criteria that is going to be implemented throughout the design phase. So a bunch of these things will have an impact on the seismic restraint design, but also on a services design, a structural design, or an architectural. And it's important to identify those as early as possible and resolve them or work through them as the design develops. So these are some of the areas that we'll be going through. So I'll quickly touch on them, and the bold ones I will go into more detail about in further slides. So the first one is identifying heavily congested areas. So that will look at sort of the main corridor areas and stuff like that. Quickly touching on to importance level. So importance level is quite key, understanding that, especially around the serviceability requirements. So they sort of tie together quite well. And what is expected. On CRL, we had quite unique requirements. So we had like critical life safety and essential life safety, and understanding those and what were the requirements for the restraint design of those. Was it a 1 in 100 year design, or is it a 1 in 25, and basically getting down to those details with the client and understanding what's required. Fire requirements is always a challenging one, not through just penetrations, but also what you're supporting off. So sometimes you will have, we had fire rated cable trays on CRL, and looking at how we could support those within a zone where we didn't have fire rated structure was a challenge that had to be worked through. So I'll go through the details of the ones in bold now. So congested zones, these are always fun to work with. So basically, these are where significant number of services or equipment are located. So they're typically around corridors, plant rooms, and risers, but depending on your reticulation strategy, it can be anywhere. So if you're running services through an office to get to another side of the building, then that can become a congested zone. The key is to identify those early, and it can be a simple idea of just getting a floor plan and just highlighting the zones that have congested services. That when the seismic engineer then comes in, gets involved, we can then look at that and start developing a strategy of how we'll manage that. Generally, because of the congested areas, conventional bracings won't work. So in a corridor, you can't just run braces at 45 degrees up. So we have to get a bit more smarter with the systems that we use. So we generally look for like I call it a combined restraint system. So these are sort of the image in the bottom right there. That's a proprietary system from Sickler, but it's basically a moment frame, so we don't have braces, and that also provides gravity support because you don't generally have room for those either in those areas. So you're looking to combine both. It's important to understand the implications with the walls and the ceilings as well, because sometimes if you've got a ceiling and you've got all these services above, you're going to have to fix your ceiling to your service support systems as well, generally. So it becomes a very integrated system. And I think we touched on the ceilings and supports there, but the key one as well is looking at the clearances. So I've gone into projects where we've got all the services going down the corridors and it's completely packed, but there's no allowance for frames. I mean, some of these frames can be 100 mil, and then you need 50 mil clearance from the sides. So you're almost talking 150 mil either side, so 300 mil off your corridor. If you've got a corridor that's only 1500 wide, straight away you're losing a good portion of that just to allow for clearances and the framing. So early consideration is key, and to help with that space planning. It might mean that you have to stagger more to achieve what you need in those zones. So, right. So yeah, and then the next part is maintenance requirements. So, like the primary structure, it's important to consider how you're actually going to maintain this building going forward. With services, they generally have a much shorter lifespan than the main structure. So, so they might need replacing or maintaining sooner. And basically, what I encourage is developing a maintenance plan very early on. So looking at how you're going to tier your equipment and stagger it is really key. So for the data centers, we need to get up. We're going to have, I think we've got 4 cable trays either side and then 3 comms trays below those. And we need to be able to get up in the middle to service those with a MEWP. Now that MEWP, size of that MEWP, accessibility and getting up and down and then moving along almost dictates where we put in some of our restraints. So understanding those requirements early is key. The other ones are how you're going to access some of the areas. So FCUs generally need access to maintain them on a regular basis. So positioning the hatches for them, and then also, is that going to clash with any braces? What kind of bracing system are you going to use for your FCUs? And the sort of image in the bottom left there is, making sure that any wall-mounted equipment is not in the way of your hatches, because it's not going to look smart when you try and lower that down. So, and there's just general coordination items. And the last sort of part there is, again, touching on heavy equipment. So locating pipes high up, any heavy equipment, if you can, locate it near or down, up or down to the structure if you can. Try not to have them suspended, 3 meters from the soffit, or it can be quite a challenge and disruptive it can dictate the seismic solution as well, especially fire pipes, because generally they have a different requirements than general services, and they can be a bit more stringent on how we have to approach those. Proprietary systems. So there are a number in the market of products available. You probably all come across these. I think the general ones that people come to are multi-strut, uni-strut, and using those. the top three ones there, as well as multi-strut, we would tend to use for your sort of smaller combined restraint systems and for your localized restraints. But when you get some of your larger loads, we like to look at modular systems. So the Cycler, FlexiStrut, mod frame equivalents. These are really helpful products because one, it allows adaptability on site. Because as we all know, as we work through the design process, what we start with, it doesn't necessarily end up getting built. So especially once we get subbies involved and they start implementing like changes or replacements for valid reasons sometimes. So having a system that can be adaptable is really good. And I'd even recommend on some projects where we're very close to be able to use one of these systems is trying to adjust the service layouts to try and accommodate these because they add so much benefit to a project. Because the next step up is using a hot roll system, which brings in a lot of cost, time, and coordination issues. So one thing I would say is to be cautious of with the use of proprietary systems, especially the modular ones, is the connections. So some of these connections, they have quite large gusset plates. So when you've got we was talking about clearances earlier, we've got the post coming down, we've taken off 100 mil for the post, we've got 50 mil clearance, and then the gusset plate could be another 50 mil. So that, and if you're really tight for space, that can be a make or break situation. So understanding how the connections work and talking that through your seismic restraint engineers is good. It's also, if possible, to understand the gravity system that will be used, because generally we'll just be looking at the seismic restraint. But if the gravity system is going to be a unistrut system or a grip, or there might be economies there to do things in and stick with one system throughout. So if you are engaged with a contractor early, it's good to start those discussions and have an understanding about, their trade prefers to use this system. So we can look at using this for the seismic restraint, and then you've got one system, one supplier. Linear service loads. So from this, when I say linear service loads, so I mean your ducts, your cables, your pipes, anything that is horizontal and linear, essentially. So it's important to get an understanding of the weights of these very early on, because it really is critical to us developing an effective solution. For ducting and pipe work, these weights are pretty well understood. I'd say that they don't vary too much from project to project within reason, and you can generally build up quite a standardized approach to them. Obviously, you need to vet that each time, but a 100 mil pipe for fire will be the same as from one project to another usually. So depending on the obviously material choice, but the comms and security trays, they're typically quite light for most buildings, but in heavily serviced buildings such as data centers, we've got some that are over 70 kg a meter, so they can get substantial, and that does add a lot of load to your frames. So do be cautious of them and just double check them early on. The main challenge we tend to find are in the cable trays for the electrical. These can vary significantly. So I've actually had projects where it's 175 kgs a meter is what we've been specified with, and you've got 5 of them. We've got almost a ton in some projects, a meter of electrical cables, which is a significant amount to try and restrain, especially if you've got like a lightweight roof to hang it from. It can become a very challenge. But typical buildings, residential, commercial, they're much lower. 15 to 25 is generally what I'd expect. Maybe a little bit higher for some of the commercials, but yeah, I think the key with the cable trays is what we tend to like to know is what cable ladders you want to use, the type, because what we have to do is check that they can actually span the distance between restraints. So we need to understand that cable ladder can go from A to B in its weak like out of plane, so it can bend horizontally between the two. So we need to understand what cable trays and ladders you want to use. So then we can do those checks early on, and that may set the positions of some of our restraints as well. So it is something we have to consider. And then we do sometimes get asked to just design for the, so we get given the low capacity of the cable ladders. So they'll give us, say, oh, this cable ladder can support this much per meter, just design for that. So, but those loads are quite significantly higher than what, so because it's just a gravity case, the cable trays are much weaker in their other direction. So it's overly conservative to take that approach and can lead to an excessive number of restraints. So I would recommend avoiding that as where possible. Throughout as part of the seismic restraint plan as well, I would recommend developing a register. So seismic risk, restraint, risk and opportunities register. It's a bit of a mouthful. It's very much like a safety and design register or a project risk register. And basically it should be prepared by whoever the seismic restraint engineer is and maintained by them. So what it does, it allows us to track progress, because obviously at the start of the project you're not going to have all the answers. So we're not going to expect you to know all the cable ladder loads straight away. You're going to have to work through that through your design. But what it does allow us to do is to track that and also align our expectations with you. So understanding that, we will need that information, and we'll need it by this time to allow us to do some design, just is quite transparent then. It also aids the contractor. It's a bit of an aid on why decisions were made. And they can get an understanding of our approach, especially when some trades come in and they take over the design. Excuse me, what's that? So yeah, and it also, we may not address all issues so during the design. So same with safety and design, we need to make the contractor aware of those risks that haven't been mitigated. So and it could be that we still don't know the equipment supplier, so it is a risk that they will need to go and engage with that and confirm that, and these are the risks associated with it. So at least they're aware of it and they know then how to manage it. So items that are usually captured on a register, these are generally, I usually start with these pre-populated because it happens on every job. So loading allowances, as we discuss, this is mainly for the structure. So if we're involved and we're not actually the structural engineer, we're just involved to do the seismic restraint, then that will be, we would need to know what we can put on the structure. So there's a lot of times where we've got roofs that have got no allowance for service seismic restraints. They've got a general service allowance of, I don't know, 15 kgs a meter squared, which doesn't really, when you look at the localized loads, doesn't really stack up. So so really understanding that early on, and then that may dictate some of the structural design and may require a stronger roof system or closer purlings and stuff like that. We also need to understand the linear service and equipment loads early on. Fire requirements, are there any services that require fire rating? Hopefully there's not many projects I've come across where that is actually a requirement, but understanding firewalls and where those are located is also important. Durability is a key one. Does it need to be galvanized? Because that will add a lot of cost, or yeah, what's the design life and time to first maintenance requirements and things like that. So primary building movements, so it's usually for the structural engineer, we need to understand how the building is going to behave if we're not doing the design ourselves. So understanding the drifts from the story, and then architectural finishes and ceilings and partitions. So again, understanding the types of ceilings we're going to be using, how we're going to brace those. Is it a fixed ceiling so we don't need to brace it, or is it a suspended one and we're going to have braces right within our corridors? So So the next one I always find fun is the BIM modeling requirements. So as we sort of growing into everything is pretty much being delivered in a 3D environment, like using Revit or equivalent, but there's also emphasis on providing BIM deliverables now as well, so smart information actually in the models, and clash detection. So we're using Revisto quite a lot these days on projects just to work through those and modeling the restraints. So there is a growing expectation that seismic restraints will be modeled because they tend to be one of the key clashes that happen during construction. So when you are asked to model, or you are asking someone to model these, I suppose it's understanding, agreeing what the principles are early on is key, because it can lead to huge overruns in cost, breakdown in communications, and all sorts. So I think that, so here's some sort of key points that I've come across in the past. So one is be realistic. What level of detail do you really need? The seismic restraints, do you need to know every nut and bolt? Generally, LOD 300 would suffice, because all you're trying to do is make sure you've got the space planning there for it and the clash detection, and the rest is covered by details. I would advise not to expect the modeling to happen too soon, because generally the design needs to evolve and develop first before we get into that. PDF markups can help. The coordination of MEP services is essential. So having someone who is over, I've been on projects where we've had different mechanical, electrical, and hydraulic engineers, and they're all just doing their own thing, and no one's coordinating them. It's not the role of a seismic designer to do that coordination. So I think making sure that there is some oversight in that, and someone is leading that and coordinating that effort. Especially another there is, if you're using overseas experience as well, that making sure that coordination is happening as well, because sometimes that can be quite a siloed effect that they have, and that can happen on sort of large projects. Understand the expectations of subcontractors. So what are you expecting the traders to do? Are you expecting them to create their own models? If so, how do we accommodate that early in the project, so we know what to expect and mitigate any change or risk? The one exception to modeling too soon is maybe the core congested zones, but these are just due to LOD 200. These are just to help with space planning. So again, allowing for those frames in corridors that could be inset, and setting some boundaries or some constraints for the services to go in with it and start laying out the trays or ducts, then that is really key and can really help sort of lead to a good end outcome at the end. Modeling of ceiling and wall restraints, while not services orientated, they are key, because they can affect the service locations, especially when you've got low ceilings and quite a high plenum. Then you're going to end up with quite large cables that may not look like the impact, but because of the length of the cables, they're going to go straight through your service runs and stuff like that. So understanding those and how they're going to behave is key as well. The last one is the last cab off the rank. So everyone likes to compete being the last person to deliver their model, saying theirs is more important. I generally find, so architects will say it, structural engineers will say it, service engineers will say it, and we're all right in some way. But I would actually argue that the last person now is the seismic restraint engineer, because he needs a fixed service model, he needs a fixed wall model, and he needs to be able to make sure he's delivering that at the end. So but yeah, so the key there is agreeing model freezes at the start and understanding that. So this could all be captured in the BIM execution plan. Right, penetrations. So so this one, it's key that you identify the locations early. I know it's very hard to tie things down when things are moving, but it's just good to understand the zones that they're going to be in. I would look to also make sure you try and set out some rules. So this will be working with the seismic restraint engineer or the building structures engineer and architect. So you want to avoid putting penetrations through your lintels, your head and jam zones of your walls, of any openings, and also trying to line openings so that if you've got your cable trays, try not to stagger them through a wall, because it really complicates how you frame out the wall and how you restrain that wall then. So if you can create a more unified approach and sort of logical system, that's always good. If possible, avoid firewalls. Firewalls can be obviously quite expensive to go through, and you might need fire dampers and stuff like that. With fire dampers, the movements can be quite limiting. So occasionally we may have to put like restraints quite close up to the wall to limit the movement of the service passing through a fire damper to meet that requirement. So understanding that a bit more early on is good. So seismic joints, try to avoid them is the first port of call. So if you can get away from bridging seismic joints if possible, then do that. But I understand that it can't always happen. When you do have to bridge it, we really need to look at the movements. This gets really complicated, especially if it's a fire-rated wall, which generally they can be, because you have quite large movements. They can be 100 mil movement or more. So understanding those movements and how you're going to accommodate them, it can be a challenge. What we tend to see is seismic loops. And maybe with your cables, you'll stop your cable short and you'll just have a loop with your cables and run through, flex your ducts. So there are ways to get around it, but it's generally can be a challenge as well. The key with some of these things as well is how those are documented. So with flexi joints and stuff like that and seismic loops, I would normally recommend that the service engineers documents them on because their information will go out to a trade and they will need to incorporate that in within their package of work. And I wouldn't leave it to the seismic engineer to document them. He may be able to advise, but just making sure it's clear in each discipline's package of work. Right. Equipment register. This is always, again, another fun one, but it's creating a register at the start of a project to understand what equipment you're going to be using. What we'd look to have is a list that, so basically we create a register. It doesn't have to be necessarily the service engineers, although it can be quite useful if the service engineers develops it. But what that needs to do, it needs to capture the size, the weight, the center of gravity of the equipment, and whether it needs to be a seismic qualified piece of equipment as well. So the keys here are, we sort of need to know the fixing points as well for the base. So that can dictate, especially if you've got an air handling unit in its position right next to the edge of a slab and the fixing points are set. So that all of a sudden then we might have an issue actually trying to get those fixings to comply. So, and looking at those, we might need to put in like a plinth or something like that to allow us to have something cast in, and start looking at those issues early. So what the list should also cover is not just floor mounted equipment, it needs to cover wall mounted equipment and ceiling mounted equipment. Now, don't always assume that you can support stuff off walls. I do have that sometimes where people just assume that you can fix the walls. If it's a partition wall, generally you'll need to strengthen that wall to support a piece of equipment unless it's really lightweight. And it needs to be factored in. It's quite hard, especially if you've got like a stud wall, for instance, to coordinate and make sure that they are putting in back-to-back studs or closed studs at locations where you've got wall-mounted equipment. And sometimes you may need to create a seismic frame independent of the wall to support the equipment that has space implications as well and can impede some of the clearances. So that needs to be worked through early in the design. And then any equipment that you're specifying, if there's anything that's unusual, like tolerances, can be one. So if you've got like some of the switchgear we do in the power industry, some of that equipment has very stringent tolerances, like 1 to 2 mil movements, which really needs to be factored into this restraint design and support design for it. So if you can think of any of those, then yeah, just let the engineer know. Seismic qualification. So with some buildings like plant and equipment, you may be specifying these on some of your projects that it needs to be seismic qualified. Now, currently, especially for SLS2 buildings, so where operational continuity is required, you generally need a seismic compliant equipment. But the issue we've got is 419 doesn't actually have a way of a suitable way of providing guidance on that. So so what you sort of have to do is follow sort of what we call the OSHPD approach, or there are a few others like shake table testing. To be honest, the best approach is shake table. You sort of shake it, fix it, shake it again, fix it again, repeat until it doesn't. So, but this can be quite costly and may dictate some of the use of equipment as well. So it's getting an understanding this very early on is key. And there are sort of set registers. So there's an OSP database where you can find out where things have been pre-qualified, but they obviously been pre-qualified for certain seismic accelerations. So you need to make sure that that's compliant to the location you're building, because obviously if you're building something in Wellington compared to Auckland, there's a significant difference in accelerations. So there are also situations where you can use snubbers to sort of dampen the seismic loads. The key with this, and we had it before, is that you need to use the snubbers that have been tested. You can't allow the contract to sub them out, or the tradie to sub them out for an alternative or more local supply, because that invalidates the testing. So just making sure that whatever you specify in there is what's been installed or been tested. So that sort of covers the main topics. The next bit, I suppose, is just sort of concluding where we've got to. So I really recommend, planning is key, as they say, I suppose. And developing a seismic restraint plan will help cover most of the issues early on, or bring them to people's attention. What I would normally look to is we'd get involved. So if you're doing seismic restraint, you'd get involved in the preliminary design stage. And at that stage, you're just sort of working through establishing the seismic restraint plan, and understanding who's doing the work, responsibility. And then generally, once you've established the restraint plan, it's usually a report followed with it. Then that goes forward. Then in developed design, you may look to develop generic details, more involvement with the architecture, which has got a bit more certainty. And then just checking that it conforms with the restraint plan. Then in the detailed design is when probably the seismic restraint design will start, I would say. This is our sort of approach. And we'll start to look at that and start to generate those models. And that can, because at that point, you've got a very good understanding of where the services are going, and we can come in and start, and we've already established those base principles. So, and then in construction, it's more just monitoring, review alterations, and understanding alternatives by trades. That can be quite a challenge still, especially if trades come in quite late on and they're not engaged early. They can change things around, want to change things around quite significantly. So trying to control that to a degree is helpful. So just to summarize, I suppose, seismic restraint is being recognized more increasingly as an increasingly important discipline. And that early engagement is key now. So we're getting councils are requiring it as part of consent. So as service engineers, I suppose we need to help upskill or better inform you of what's required from our perspective, and vice versa. So it's going to create a better collaborative environment that we're going to have to work through. So on that sort of ends my presentation. So
That's awesome, Chris. We have a couple questions in Q&A section. I'm not sure if you want me to read it out or you want to go it one by one yourself.
I'll just pull them up 1 sec now. It's just taking its time to load up.
Yep.
Why it does that? I can see Chris raised one about the 7.5 and the 10 kg. So the 10 kg is from 1170.5 before the amendment. But in Amendment 1, they reduced that down to 7.5. So that's generally what I would advise that we use, although it's not cited. So, legally you don't have to. I hope that answers the question. So are you able to go over clearances between ceiling mounted services and ceiling? Some commercial kitchen hoods. Do we need 25mm clearance between? Sorry, let's see more. Between the hood and the ceiling where it penetrates the ceiling, leaving a gap. So yes, if the ceiling is braced, you'll need to provide a seismic gap 25mm. The key there is making sure the ceiling is braced. The tolerances are much higher. I didn't have it in the slide, but is making sure that it's a braced element and the kitchen hood is braced. Obviously, it should be. Then you can limit that down to 25mm. Please, can you talk about percentage MBS ratings of existing buildings and existing services? So when you're doing DSAs, there is part 10 of the seismic assessments covers S and S, so secondary steelwork, secondary structure and non-structural items. Now, if you are to say a building is 67%, you sort of need to demonstrate the service restraints elements are also 67%. So we was doing work for foodstuffs where we were having to do that with all their stores, and that was also demonstrated. With hospitals and IL4 buildings, the recommendation is that you need to bring up the seismic restraints to 100%. So now that is a challenge, especially in a hospital environment where it's very congested zones. So, but that's the recommendation. It's unfortunately it's not written down as a requirement because there's a little bit of ambiguity around that. But that's a general approach that I would take, is that those do need to be 100% and it does need to be checked as part of the DSA. So, Freddie, Travis, so are you able to clarify if supply and return cushion boxes require seismic restraint? Again, I suppose it's depending on the weight of them and where they're sitting, because if they're above 3 meters, so there's sort of those requirements of what don't need restraint. If it can fall within those, then maybe not. But again, it will be a discussion about what those are and where they sit. Because if they're high up, they've got a higher chance of impacting someone, and they will need restraint, or at least tethering to the structure. So Brenda, so we are constantly pushed for reducing ceiling spaces by clients. Can the seismic clearances from services to ceiling be reduced to less than 50mm if the ducting, pipes, etc. are restrained? Generally, I'd say no. So I'm saying this. I'd say you've got to maintain the restrictions in. Just pulling it up, so it's quite a useful image. So you've got to maintain greater than 50mm. So it's, sorry, there we go. So yeah, I would struggle to, I would say 50mm is a minimum. A lot of the failures at the Christchurch were where ceilings were popping through and services that clearance wasn't maintained. So I would emphasize trying to maintain that, and that the ceiling needs to be kept lower. It is a constant debate between architects and service engineers and structural engineers, because especially when we add in the support structure for it. Brenda, so for the clearance from the structure for ribbon infill 4, where does the clearance start? At the bottom of the floor or the bottom of the rib, or it depends where you're supporting from. So it's where you have the support from. So if you're supporting it from the floor, then that's your 400 mil, say, for a cable ladder. But if you support it from the ribs, that's your support point. So generally, I would advise not to fix into the infill. Depending on the way of the surface, if it's really light surface, it's probably not an issue. But generally, your infill floor is quite thin, and so your anchors are very limited of what they can do. And there's also debate about whether you can actually use the actual board, the ply board, for capacity. And there's a few checks that have to be done. We'd normally advise fixing into the side of the ribs and trying to do that, or looking at the base of them. So I think was new post. If you use table 3.1, sorry, so Douglas, so thanks for the percent MBS clarification. If you use table 3.1 in 1170, which is 5 kPa for plant rooms, may be much higher than the actual known weight of the existing equipment, resulting in a theoretical low percentage. Although, while based on the actual plant weights, the percentage could be okay. How do you handle the situation? So the idea of the floor weights is that things can change and flexibility. So if you look at what's currently there and you assess it for that, then you're not allowing any flexibility for future changes. So generally these probabilities of live loads and stuff like that, that's how they would come about. It's more statistical than it is. But for air handling units, you could argue that you could look to reduce that, but it's understanding, agreeing that with the clients and saying this area is no longer, this is designated as a plant area, but this is the limitation of it. You could approach it in that way by limiting the use, essentially. But yeah, it really needs a client to understand what they're using the space for, is what I'd say, and that discussion with them. And also engage in the structural engineer who's doing the assessments and that. So their buy-in's key. And as you'll find with structural engineers, we all have different opinions of the same thing. So, so Stephen Joy has, hi Chris, can you discuss challenges, methods associated with seismic restraints for major plant rooms with structural steel roofs as opposed to fixing to concrete slab soffit? Structural steel roofs can be really difficult to work with because especially if the seismic restraints aren't considered soon or the plant restraints aren't considered soon. So because you generally have quite large spaced purlins. I've been on jobs where there's purlins in a space that's 600, and I've got to support quite heavy services, and we have to put in additional steel work to do that. If possible, in plant rooms, try and take it down to the slab because that's where the capacity is. But where you do need to suspend services, it's understanding those routes early on and identifying them to the structural engineer. Because in those areas, it may be they replace some of the purlins with steel work to provide sort of a grillage to fix to. And then they can work through that, and the connections need to be strengthened up as well to make sure they can take the seismic loads. But it's an ongoing challenge, I'd say. So Alan Sharkey, in proprietary systems for services supports, who would typically pay for this system? Example, builder, mech, electrical. It would be the contractor would normally pay for it. So it would be the seismic restraint engineer would normally specify it. There are some early engagement with a builder or contractor is key there because supply issues for some of them can be a challenge, and the cost of some systems can be quite significant. So compared to other systems, but there are pros and cons of each one of them. So, the Sickler system is an amazing system. It costs a little bit more, but it has higher capacities. So we'd look to use that for heavy serviced areas where we really need to get to work, and the connections they're not as intrusive. So it has a bunch of pros that we look to use. Mod frame, probably looking at lighter loads, but so sort of those mid-level service weights. But the cost itself would sit with the contractor. So, and they may put forward equivalents, so which would need to be discussed. Yep, and I assume, Mac, that yeah, that shouldn't be a problem if we share the video, Anna.
Yep.
I think that's answered.
Judging by the number of participants and questions today, I can tell that seismic restraint is a very hot topic, and we probably need more than 1 hour to dive into it in more details. But yeah, on behalf of everyone, I would like to say big thanks to Chris for sharing his knowledge and finding time today. And if you need Chris's help, I'm sure he will be more than happy to help and assist you with any seismic design.
Yeah, definitely. Yeah, it's been a pleasure. I had to. There was a lot more we could have gone into, but it's yeah, definitely an interesting place to be. So, thank you for the getting me involved, Anna. It's been a pleasure.
Thank you. Have a lovely day, everyone. Bye bye.
Thanks, everyone.